Alright, let's start Let's start with two big errors, one being failure to set it back to normal speed, and the other being failure to use capital letters. Because BBC Basic commands all have to be in capitals. Having started with that failure, let's start, if this works into browser at the same time as recording this window, with a shout out to Science It Out for
version 2 of the video about the difference between what flat earthers think Coriolis is and what it actually is.
because that's an excellent video and I really appreciate it, and the follow-on videos and other animations that were made. I'll try to remember to put a link in the description. Having said that, next one is a call out. I love getting to do this. This is so nerdy. But technically it's there.
Well, if you draw a line between the 2 points on Earth that are 12 noon and 12 midnight, you get a line that's perpendicular to the orbit of the Earth. It moves in its orbit about the Sun in a counterclockwise motion.
No one's called it out yet. It's actually only perpendicular at the solstice. In between, because Earth's orbit is elliptical, it's very slightly off. Not far enough off to actually matter to what he was saying, but it is slightly off. Nerd point for me. Thank you, Bob the Science Guy. Right. What was this thing actually up for? This was actually open for this very simple little program. It has a line 31 in it because I changed the layout when I decided to add some extra text in the display. It has a couple of missing lines because I removed something that wasn't really worth having. There's a commented out line 20 which isn't needed anymore, which I never got rid of. Put some text on the screen. For every latitude from 1 to 89 in steps of 4. Set the latitude in radians to be the radian equivalent of the latitude in degrees, like duh. Start the altitude at 4.2 E7, also known as 42,000 kilometers. Then repeat means from here down to the until, keep doing everything that's in between. The strength of gravity is 3.986 times 10 to the 14 divided by the square of that altitude. Radius, altitude, whatever. We're treating Earth as a point mass here, so they're treated as the same thing. The component of gravity that is in towards the axis of rotation is local gravity times the cosine of the latitude. And BBC Basic works in radians, which is why we have radians latitude. Gx, gravity toward the equator, is the strength of local gravity times the sine of that latitude. Basic trigonometry. Sen, the centripetal acceleration required to keep a thing going round in circles in that position, is the altitude times the cosine of the latitude divided by 188,058,462. Obviously. Of course. The actual calculation there is that the centripetal acceleration is the square of the velocity divided by the radius of the circle. Square of the linear velocity, that is, divided by the radius of the circle. The linear velocity is the circumference of the circle divided by the time it takes to go around it. The circumference of a circle is 2 pi r. So now we have 2 pi r over r all squared divided by r. And when you do all the maths, you get that weird number. I hope. Nin. Net inward acceleration, which is the gravity pulling you inwards minus the part that is used up because you need that much centripetal acceleration just to go in a circle, is the force is pulling you inwards relative to something going in that circle. It's just the difference between the two. Net G mag, this is Pythagoras, it's the square root of the sum of the squares of the net inward towards the axis force and the net toward the equator force. That tells you how much it would actually weigh if you were standing on the surface of an object rotating at the same rate as the Earth at that latitude and that distance from the centre. And that is a geocentric latitude, not a geodetic latitude, for people who are keeping track of the difference. Net G ang, the net gravitational field, force, whatever you want to call it, acceleration, angle, the angle between the direction of your weight and the plane of the equator, is, in degrees, is the degrees equivalent of the radian angle, whose tangent is G eq over net in. Fairly simple trigonometry still. Difference. The difference in directions is net G angle minus latitude. This usually works. It gets a little weird if you get carried away. Here we go back to line 80. Yeah. If at line 80 you put in, say, 1e8, because it's a nice, obvious, simple number, 100,000 kilometres, the problem is you're outside geostationary orbit and your weight is a negative number. Yeah. You'd have to glue the scales to the surface of an incredibly strong object and then cling on for dear life to the top of the scales, and they would read a negative weight. That's what I mean by weight being a negative number. Its direction, your net weight, is actually in a direction that's not opposite, but it's a heck of a long way from the direction of gravity. Starting at 4.2e7, you are inside geostationary orbit, and your weight starts out as a positive number, which makes it a lot easier to understand what's going on. And then we have print tab commands. There are some people thinking, gosh, I haven't seen one of those in 40 years. Yeah. This code is older than some of the flat earthers it's debunking. 02 just means no columns across and 2 rows down. Print the latitude, 15 columns across and 2 rows down. Print the altitude, no columns across, 7 rows down. Print the strength of gravity where at the current location. 15 columns across, 7 rows down. Print the magnitude of the net gravity at the current location, which can be very slightly less, just very slightly. And then you have the gravity angle and the difference between the two directions, exactly corresponding to the headings that were printed by lines 30 and 31. Line 240, altitude is altitude minus 1e3, also known as 1 kilometre. 250 until altitude is less than 5e3. When we get down to 5 kilometres from the point mass Earth, it doesn't need to go back to line 90 and go through all that again. It can move to line 260, which says next latitude. 270 end. 270 end is a relic from when there was actually stuff after the end of the programme, which it got to from line 230. Procedure, but I deleted that because it wasn't really helpful. So here we have a 1 degree north latitude, or south latitude, either way. Started way out at nearly geostationary, that radius. You see, gravity is a piffling 226 millimetres per second, but your net gravity is only 5 millimetres per second because you have that centripetal acceleration required. You're very nearly in orbit there. 5 millimetres per second is how fast you'd be falling away from an object in geostationary orbit that's just a little bit farther out than you. And then, as we get closer and closer to the Earth, not falling. This is just doing the calculations for a series of points. There's no trajectory here. You can see the strength of gravity is very slowly increasing. We're heading towards 23 centimetres per second there. Coming up. And also net gravity, because we're still being held above the same point on the Earth, but we're closer to it. So we're going around, we have a smaller radius, we're going around at a lower speed, that centripetal acceleration is decreased. Net gravity is nearly up to 1 centimetre per second there. It's getting there. It's coming. There we go. There's 1 centimetre. Gravity angle, it started out at quite a large number because the centripetal acceleration, while it was tiny, was quite big compared to the tiny gravity. And most of what was left was a lot of what was left was the component towards the equator, which isn't cancelled out by that centripetal acceleration. So the gravity angle was quite large. As we get further and further in, the gravity angle is decreasing. You can see the angle from the radial is, well, we're only 1 degree north, so it's pretty much the same thing as the gravity angle. It's just minus 1 degree, which out of 30 is a pretty small change. I'm going to go up to the speed menu and change this to 100 times speed. You can see the kilometres of the radius are counting down there. And suddenly it looks like it's going 10 kilometres at a time, but occasionally the kilometre number changes. Because it's not quite running at, like that. Not quite running at an exact multiple of 10 iterations per frame. Don't worry, I'm not going to make you sit through the whole thing. There we go. 334 something. 33,400 and some kilometres from Earth centre. The angle between net gravity and radial dropped below 1 degree. And gravity is still it's slightly more than 1 foot, but it's a lot less than half a metre per second. We shall now skip some. I slowed it down to 5 times speed in the hope that you'll be able to see what's going on more clearly. Instead it looks even more frantic. But you can probably see a few errors showing up here now. We're still on latitude 1 degree. This is taking quite a while. Radius is down to 12,500 kilometres. That's fine. If you look at gravity, everything is tumbling like mad apart from that 7 on the end of it. What's happened? Where it was saying 0 point and a certain number of figures, the decimal point has moved 1 place to the right. We've gone past 1 metre per second. We're currently at 2.7 something, but we're still showing the same number of significant figures. So those are being refreshed, but the 7 that was there when it was the last significant figure hasn't been removed. If you look at net gravity, we're on 2.8. It's still slightly less than gravity. Over on the right, we see 7 negative 2. This is a sort of accumulation of 2 such errors. It did say E negative 2, which means divided by 100. When it jumped to tenths rather than hundredths of a metre, it stopped bothering with E negative 2 and it started doing 0.0 blah blah blah. But it left the E negative 2, except the last digit overwrote the E. Now that it's gone to whole numbers, it's left the last digit, also a 7, up there. And then we have the gravity angle, which is running fine, and angle from radial, you can see it's mostly E minus 2, meaning times 10 to the negative 2 per 100. It's mostly 1.44 hundredths of a degree. But sometimes it's saying E minus 22, just for a moment, just for a tiny instant. Maybe if I slow this right down to normal speed, this is how fast an actual BBC Micro would do it. There, you can see the minus 22, which is a really, really small fraction. Like, milli is E minus 3, micro is E minus 6, nano is E minus 9, pico is E minus 12. I think femto is minus 15. I don't know minus 18 and minus 21. Minus 22, well, E minus 22 is times 10 to the negative 22, which is equivalent to per 10,000 million. Obviously, that is not the actual answer. The same thing is happening as on the others, where the minus 2 is just sitting there. But here, sometimes it's giving us, I think it's 9 significant figures, and sometimes it's only giving us 8 because it's an exact number to 8 significant figures. So it stops after the 8th one and immediately prints the E. And the 2 from the previous one, which had 9 sig figs printed, remains, and it looks like E minus 22. So, bit of a glitch there. Probably I should be putting a black rectangle over all of that text each time. And while I've been talking, the radius has dropped below 10,000 kilometers, and you can see that's now done the same thing. It has left the last 0 in place. Still quite a long way out. We shall give it a while longer. Skip ahead. Skip ahead to there. Official border of space, 100 kilometers up. We are officially into Earth's atmosphere. We are into thick enough atmosphere for aerodynamic control to be usable. You could steer with fins. And there's 6378, and we're at 9.81 meters per second. How's that for an astonishing coincidence? The maths just happened to give, a number that conforms to observed reality. And you'll notice over on the right now, we've gone to E minus 3. The angle from the radial is now 3 millidegrees. Skip. Inverse square law coming up. Just went past it. Well, I just went past half, and about there is 1/3. 1/3 the radius, 9 times the gravity. Getting very close to the point mass here, and you can see the gravity is increasing. If I take that speed down to real time, pause there, 1024. Or is... No, it isn't. Is it? Probably 1024 kilometers. 380 meters per second, or 380 newtons per kilogram. (1,022 kilometers). We're already up to 381.6, which means, actually I should be looking at the net gravity, not the actual gravity, but as you can see, there's not much in it here. We're still talking about a difference in the centimeters per second. In fact, 5, pretty much, centimeters per second. 50 millimeters, or 2 inches per second difference caused by that centripetal acceleration. But you've got those 2 newtons per kilo, 1/5 your weight difference in that distance. We're getting into scary number territory. down below 1,000 kilometers. Yeah, angle from radial is now down to E-5. That is tens of micro degrees. This is no one gives a damn country. Because when you're that close to the centre, one, the gravity is incredibly strong, and two, your path around it is very small, so your inward acceleration, centripetal acceleration required to follow that path is much lower. And skip. Down to the last 80 kilometres. Gravity's getting into some really scary numbers here. I'll pause it at 11 kilometres radius. Extra zeros on the screen shouldn't still be there. You can see over on the right, the angle from radial is now down to -10. Times 10 to the -10, so that is tenths of a nanodegree that's in. I wouldn't worry too much about tenths of a nanodegree. Nobody's going to measure them. The magnitude of gravity is 3294214.887 newtons per kilogram, or meters per second. And the net gravity is exactly the same because, that's 10 significant figures. Right, to 10 significant figures, that centripetal acceleration part just doesn't show up. Centrifugal force, if you want to call it that. It's not even in the first 10 significant figures when your gravity is up there in the, yikes, 3.3 meganewtons per kilogram. Holy cow, that's a lot of gravity. If I can just get one frame forwards, we go from 3.294 meg. There we go, to 3.986 meg. It's roughly 700,000 newtons per kilogram in 1 kilometre. So I call that 700 newtons per kilogram in 1 metre. Which, that's an interesting problem, because if you have 1 kilogram of sugar connected by a string to another 1 kilogram of sugar, or a litre of Lucozade in a plastic bottle is about 1 kilogram. Like a sugar, about 1 kilogram. One of those has, the one that's nearer the point mass has more weight than the one that is farther from it. This is perfectly normal. This has been true of any of these distances that we've calculated. But here, the difference in weights between those two sacks of sugar, bottles of Lucozade, whatever, 1 metre apart is equal to, if I've done the maths right here, 70, the weight of 70 kilos, 70 bottles of Lucozade, 70 bags of sugar. A full-grown adult on the surface, at 6,371 kilometres. Meet tidal forces, in other words. This is where the difference in weight from the inside to the outside of a satellite can actually cause it to be torn apart by its own weight. The bottom falls off the top, in effect. Of course, here it's not in orbit, it's sitting still, but the difference still applies. And our latitude has increased. We are out to 5 degrees latitude. We are back to 227 millimeters per second of gravity. And 20 millimeters per second of net gravity, because we're nearly in orbit. 76 degrees from the plane of the equator. that you'd actually be pulled, which is 71 degrees from radial. It's already down to 72 and 67. Skip. And at 29 degrees latitude, we see pretty much the same thing. 226 millimeters per second of actual gravity, 100 and just about to be 110 millimeters per second of net gravity. And it was very nearly at right angles. Net gravity was pretty much straight towards the plane of the equator. Coming down towards 20,000 kilometers radius and coming up towards 1 meter per second of actual gravity. There's quite a difference there between actual gravity and net gravity. There's 1 meter on actual. And on net, by which time we're up to 1.08 meters per second of actual gravity. Big difference, really. You'd notice and stuff with accurate enough scales. Also, still 2 degrees between them in direction. What I have just noticed is that this is never going to get to 51 degrees latitude, so the angle of inclination of the ISS orbit around the Earth isn't going to come up among these results. Shock, shock, horror, horror, what a tragedy. No one cares. Skip. And why does no one care? Because it doesn't actually matter, because the ISS isn't held above 1 point on the Earth, so the centripetal part is irrelevant. It's at about 400 kilometers altitude, which puts it at either 6778 or 6771, depending how they worked out that number. And I may have started recording again just a little bit too soon, because now I've got nothing to talk about while I wait for another 100 kilometers. There we go, 6771. Actual gravity 8.694 meters per second, net gravity 8.666. The number of the beast. Hell and fire were spawned to be released. I'm coming back. I shall return, and I'll possess... Sorry, excuse me. At an angle of 29.1 degrees, which is 1 degree from radial. We can just call it 8.7, can't we? Just, avoid all the awkwardness, just call it 8.7. Actually, that would be 8.667 if you were reading it properly. Or 8.669 if you're just 1 kilometer lower. Very short. Skip. To latitude 53 degrees. Just actually quite a long skip. Somewhere over England. If you're at England's longitude, and not over England if you're at anybody else's longitude. And we're seeing pretty much the same thing. 220 millimeters per second actual gravity, but only 180 net because of centripetal acceleration. Pretty much 90 degrees to the plane of the equator, because it was very nearly at geostationary orbit height and going around it, cancelling out most of the gravity in the direction towards the Earth's axis. We're already down below 36 degrees between direction of gravity and direction of net gravity, but that's not really all that amazing, because we're only 36 degrees from the pole. That was the word I was looking for, the pole. by which of course I mean North or South Pole, not, that Polish kid over there. And if it's the South Pole, then 53 degrees is not England's latitude at all. It's maybe somewhere in Patagonia or New Zealand, and maybe it's south of both of them. Although according to a recent video by one Flurf idiot, or several Flurf idiots, I should say, 38 degrees south is too close to Antarctica. Yeah, guys, we actually know where Bass Strait is. It's north of Tasmania, and you can visit Tasmania. Anyway, enough about those idiots. We are coming up on 0.1 G, where G is 0.1 G. We are coming up on 0.981 meters per second per second. So I shall slow down to 1/100th of that speed in order to make sure we don't miss the moment, in case anyone wants to see it. Probably still miss the moment. I'll sneeze or something. Maybe 5 times speed is, slow enough. You can still see that third digit clicking, can't you? That's close enough. There we go. At 20,149 kilometres. Well, it's actually 0.982 now, but close enough. But that's actual gravity, and we need to go forwards a little bit more. Little bit. And that's close enough. 19,791 kilometres net gravity is 0.981 meters per second, with most of 3 degrees between those two directions, because we are such a long way from the equator now. Skip. Actually, I've been saying all this stuff about what you can probably see, and you probably can't see some of it because I'm only recording at 5 frames per second in order to reduce the upload times. Anyway, just come past the ISS orbit, and we're a little bit too far from the equator to have gone actually through the ISS orbit. It doesn't get this far from the equator. But, that altitude. And we've just gone past 9 meters per second of actual and net gravity. This latitude surface radius is about 6364 kilometers, I think. And that's radius to the surface, not radius of curvature of the surface. There's 6371 kilometers. There's the volumetric mean radius, 9.82 of actual gravity, but just on 9.81 of net gravity. And at 6364 kilometers, it's 9.84 actual, 9.83 net, with 95 millidegrees between their directions. Big skip. And we're at 89 degrees latitude, where you'll see, if I pause it, make it really obvious, There is still a difference there between gravity and net gravity, but not in the first 4 digits. That 4th digit changes from a 1 to a 2 because of rounding. But if you're expressing it to 3 significant figures, no, it's the same thing. And that means that, well, this is because we're 89 degrees from the equator, so our actual distance from the Earth's axis of rotation is tiny, centripetal acceleration is tiny, it can be pretty much neglected, and that means both the actual gravity and net gravity are in the same direction. Net gravity, it's a good enough name for it. They're within 1 degree of each other again, just as they were 1 degree from the equator, except, you know, we had to get lower than this for it to be within 1 degree when we were close to the equator, because there was so much centripetal acceleration there. Here, they're less than 1 degree the whole way down. Big skip. And coming down very near the pole, getting close to the 6356 kilometre radius. Well, 6357 is closer at the pole. 6371 going past, and I missed 6356 because I'm getting old and slow. At 6354, which is, you know, most of 3 kilometres underground at the pole. 9.87. 9.87. 9.872857 really, and 576, so it would round to 58. 9.872847 net. And we're down to 3 millidegrees between them. I am now going to make a lot of changes to this program to make it do something